So I have a full-packed presentation, so I'm gonna go quick today. I hope it's gonna be interesting. Let me first say this is joint work with my colleagues Ruben and Asgeir, but it was initiated by 3 master students, Ingvild, Annette and Marit, abbreviated usually as AIM. So this work has been done in or financed by 2 large research centers in Norway. That's the National Research Center on Energy Transition Studies, NTNU, and Research Center on Mobility Zero Emission Energy Systems, MOSES. If we can get this moving. Just a quick outline to give you an idea of the presentation today. So I'll start with a background in why we're interested in modeling national freight transport models. And I'll then quickly dive into the literature, what has been done, what is the state of the art, what are governments using currently. And then we identified a gap in the modeling part, which is why we developed this model STraM. And I'll conclude with some illustrative results. So the background here is that the freight transport sector accounts for approximately 10% of carbon emissions globally, and these emissions are hard to abate in the transport sectors, especially for long distance transport. That's a big issue. And on a global scale, we see that the demand for freight transport is expected to rise. We see it's going to triple up to 2050 on a global level. So there is a motivation to decarbonize the freight transport sector. Then the question is, how are we going to do this? So one option is to switch to new fuels, maybe other modes of transport. Maybe we can have a mode shift to rail or sea. In any case, we need infrastructure investments now to make this happen. So what are we interested in? First of all, the main question which is overarching this whole presentation is how can countries achieve low emission freight transport systems in a cost efficient way? And then we have some sub questions following. So which technologies or which fuel technologies should we use? Which infrastructure investments in roads or railway lines, terminals, etc. Are necessary? And how is this whole thing impacted by uncertainty? We don't know exactly how technology develops. What will be the cost structure of hydrogen in 10 years? This is not clear. How much ammonia can we use? And when we take a step back, the main motivation for this work actually was to provide input on these necessary infrastructure investments for the Norwegian National Transport Plan. This is a 10-year investment plan by the Norwegian Parliament, which is set up every 4 years for investments in all modes of transport, so rail, sea, and road. And with the research institutes or research centers, NTNU and MOSES, we aim to provide input to the National Transport Plan. This is where we started 2 years ago, and we looked at, okay, what models can help us to answer these questions, and then you quickly get to national freight transport modeling. So every country in the Western civilization, at least, has a national freight transport model. So this is well established, has been researched for a long time. However, when we looked further into the details, we see that there is a trend towards highly detailed models that mimic the current system very well. They are static models that model the system as is. And they're useful for detailed analysis to figure out, okay, what happens to the transport system if we build this bridge? What if we expand this road? Then you, in a way, can simulate the current transport system. It's based on a 4-step approach. I won't say too much, but the first 2 steps aim to generate demand for transport between origin and destination pairs, so that just between cities or nodes in a system. Then in a modal split, this demand for transport is translated into a demand for transport within a mode. And then the final step is for this transport within a mode, we have to figure out which vehicles are going to transport the goods on particular routes. So when we looked into this, we thought, okay, it's very useful, but it's not so suitable for problems of a strategic nature, where we have a long time horizon and we try to develop or model the development over time. Another important strand of literature is within transport modeling is network design models, and they explicitly model infrastructure investments that are not explicitly modeled in the state-of-the-art national freight transport models that are currently in place. Here they do it, and they also model the operation of the network on an aggregate scale. We do this to evaluate how well a transport system performs, so if to assess the feasibility and the performance. Finally, I would like to note the STAN framework, already developed early in the 90s by Guyalat and Krenich in Canada. This is actually a national freight transport framework based on a network design model. However, it's still a static model, one aggregated time period, the current system as it is, and no long-term uncertainty. But this is something that we can build on, and that's what we're aiming to do. So we identified a gap, also highlighted by Meersman et al., that these static models have difficulty with structural changes over time, and especially uncertainties. So there's a need for a framework that actually can capture these elements. And that's, we want to have multiple time periods. We want to have the explicit modeling of new fuel technologies, which also is non-existing in the current state of the art. There only the modes of transport are included. And we want to have long-term uncertainty. So that is what we developed, a model that takes this into account, and we call it STraM. It's a strategic freight transport modeling framework. It's openly available on GitHub, so please have a look. And we also have a preprint and archive if you want to read some of the details after the presentation. So when we think about this in academic terms, then we can classify this in this way as a strategic, stochastic, multi-period, multimodal, multi-commodity network design problem. That's a whole mouthful. I guess it's easier to visualize this later on. I can say that STraM mainly focuses on the last two steps in this four-step procedure. So figuring out which modes and fuels are going to perform the demand for transport. While step 1 and 2, we simply take it from the existing Norwegian freight transport model. And that is the estimation of the demand for transport. Okay, overarching, what is the problem we look at? We take the perspective of a social planner, usually the government, who can or who wants to minimize system costs and can do so by investing in infrastructure. So that was the railways and harbors. And also we have to take care of the flow in the system. We have to make sure that we have a feasible and efficient transport system. So those are the decisions that we have. Let's look at some figures. So what is this model? We take the case of Norway to illustrate STraM, but it can be applied to any national country or even several countries. We look at zones, big regions, here highlighted by the counties in Norway. And we model the transport between zones. So the transport between the Viken, where Oslo lies, and Trondheim. So we get long distance, the demand for long distance transport. And yeah, there is some assumption that the first mile, last mile most likely will be electrified and done by truck anyhow. So then when we have this system, we can construct this graph on the right-hand side, which visualizes the modes of transport that can be chosen between all nodes in the system. And the special thing with Norway is that we have the coastal shipping between almost all cities. It's only Hamar that doesn't have a harbor. So this is a special case, and let's say the dark red lines depict railways going from south to north, and there are some connections also on the east-west from going from east to west. That's the transport system, and this is capacitated, so we cannot transport as much as we want. We have to limit the transport within, especially within Unreal, but also the amount of transport going through nodes where we have to adhere to the capacity of terminals and harbors. But we can invest in extra capacity, so those are the decision variables that we have. So then I was talking about demand for transport. What does it look like? Well, we have this is all the aggregated demand for transport in an origin node. That's the green, and then it can go to some other node, the red one. So visualizing the demand for transport, and we do this for different product groups. So product group shares the same characteristics, and most likely when you identify a product group, you know what kind of vehicle you will need to transport this product. We do not only do this for the system as it is now, not only 2023, but we have a demand for transport in the upcoming years up to 2050. So in our model, we have a timeline with 5 time periods, and we assume some steady state operation between the years. Then given the system and the demand for transport, we have to transport these products. That's the next step. And then we can do so by transport modes and corresponding fuel technologies. So this summarizes what is included in the model. So we have the modes rail, road, and sea. And then we categorize the fuel technologies into 4 overarching groups. That is the established technologies with marine gas oil, LNG, and so on, contact line for rail. And then there are groups for battery-based, hydrogen-based, and biofuels. So we assume these technologies somehow develop in the same way over time. And as I mentioned on the previous slide, given that we have a mode of transport, a fuel technology, and we want to transport a specific product, then this points towards a specific vehicle, maybe a battery electric truck for general goods. So then we know the cost structure of that vehicle, or this is what we assume. Okay, so we were talking about fuel technologies and what we consider there. And here I want to state that we do not know what happens to the cost structures. We do not know how the technologies will develop. And this is why we take into account uncertainty in our model. We take a 2-stage stochastic programming setup, where I visualize the scenario tree on the right-hand side. And in the first 2 time periods, we assume this is still deterministic parameters. We know the costs of the technologies. However, for the future time periods, we construct various scenarios describing future possible realizations of the cost structures, but also the rate of adoption of technologies. We do not want to have different futures for all combinations, so we define groups of technologies, and those were the battery-based, hydrogen-based, biofuel-based. And then we can have optimistic, base, and pessimistic scenarios. So this leads to the following scenario tree. A point I just mentioned was the adoption of new technology. So you cannot simply start using 100% ammonia in shipping. This takes time. Technology has to develop, and technology adoption is usually modeled by means of this seminal base diffusion model. So this is something we would like to include in the model, and we have done so in this 2-stage framework, where we get these nice S-curves. We know the maximal uptake in the first stage, but in the second stage we have to constrain. We're not entirely sure how the technology will develop and what the maximum adoption level can be. So the paper goes into more details how we actually managed to include this in the model. Okay, then on a high level, what does the model exactly look like now with the pictures in mind? So we make these strategic investment decisions, and we have to also operate the system, deciding the flow of goods between nodes in the system. And then this social planner, the government, would like to minimize discounted system costs. But there's some risk preference there. We do not only care about minimizing system costs, we also would like to perform well in all these possible futures. So we include a mean CVAR objective, which is just a weighted average of the expectation and a conditional value at risk. Okay, mathematical model in words. Let's see what we have. We of course have some boring bookkeeping constraints, and here we have to make sure that we fulfill the demand for transport in the system in each time period. We have to adhere to the capacity constraints and so on. I can highlight this non-anticipativity constraints, which take care of this thing that we don't know what is going to happen in the future. What is interesting in the model? Well, we've added several elements that are novel or in any case, quite interesting. So I highlighted the base diffusion model, technology adaptation, and that we restrict the rate of adoption of a new fuel technology over time. So we take into account the adoption share in a given time period, impacting how much can be adopted in the subsequent time period. Also, we have fleet renewal constraints, merely stating that switching to a new technology takes time. Given that the lifetime of a ship can be 20 to 30 years, it takes time to renew the fleet of ships. But also for trains, we have long lifetimes and trucks a bit shorter. Finally, we include fleet balancing constraints, not always done in freight transport models, which state that we also have empty vehicles in the system. So you can imagine when you drive from south to north with your load of goods, you also have to drive back, which if there is not a balance in the system, then you get empty vehicles. So we model these empty vehicles explicitly. Finally, I can state that we do not model emissions explicitly, so no hard or soft constraints. This is taken care of by policy measures, so just carbon price, carbon tax. For the operations researchers in the room, we have a path flow formulation to reduce the complexity or computational complexity of the model. And yeah, the details of this path generation algorithm are in the paper as well. Okay, now the interesting stuff. What can we do with this model? That's going to be interesting. Some nice figures illustrating the usefulness. I don't want to go into too much details. That's going to be future work where we really come up with policy insights for Norway. But let's see here. First, some initial figures. So on the left-hand side in figure A, we observe investments in edges and nodes corresponding to railway lines or terminals. And we see significant investments in charging and filling infrastructure in the first two time periods. But also there's some investments in upgrades for railway lines, so electrifying existing railway lines. Looking in the second stage, we have these black arrow bars denoting the standard deviation across the future scenarios. So depending on the realization of our uncertain parameters, we can have quite different investment structures in the second time period, or the second stage of the problem. In B, we highlight transport costs. I'll skip that one. Whereas in C, we see that we observe the emissions for each time period. And we've also highlighted the emission targets from the Norwegian government. And here we see a pessimistic picture that on average, we do not meet the emission target to 2030, not even in 2034. And in most scenarios, we do not even achieve this with the current stipulated carbon price, that is. Other results we can highlight is when we dive into the mode fuel split. So which modes of transport are being used, and for each of these modes, which fuels are going to be used. So some general observations here, just seeing that both on rail and sea, we see an increase in the transport work and a little bit less increase on road. But I will not go into the details of this. Then we can look at the geographical level of the problem. So on the left-hand side, we visualize the aggregated flow of transport for all product groups, and visualize this according to the mode of transport. So a lot of transport in Norway goes by sea along the coast. Almost the same share is on road, and a few percent of it is by rail. Then the interesting plot is on the right-hand side. This is a difference plot showing the comparing 2050 to 2023. And then we only highlighted differences in the operation of the system. So the green lines represent an increase in transport on that arc, and the red lines represent a decrease. So what we see there is there's an increase on coastal shipping for all connections. In general, decrease on road, but there are some corridors, for example, between Oslo and Trondheim, where we do see an increase. And also the connections to Sweden see an increase in transport. So that was the flow of goods. We can also look at the actual investments and model them on geographical resolution. Interesting observations again here, where we invest in 23, especially in the radial network from Oslo to the cities along the coast, but not so much in the connections along the coast. And in 28, the system is reinforced towards Sweden and very little up north. Okay, the value of uncertainty. If we go back, why do we include this scenario tree and then go this approach, take this approach? In the stochastic programming literature, there's a metric, the value of stochastic solution, that says something about the value of doing planning under uncertainty with deterministic planning. This is defined as a difference between the expectation of the expected value solution and our stochastic programming solution. And when we quantify this, we observe that we have a 6% monetary gain, which is substantial. And it corresponds to actually reduction or 5% lower emissions. So there is value to planning under uncertainty, both in terms of money and emissions. The figures below here show the difference in investment structures. The main takeaway here is that in the stochastic solution compared to the deterministic one, we postpone some investments to the second stage. And we wait until we observe which technology really our scenarios realize, and then we invest in the right technologies. So this gives some flexibility, and that's what's giving the monetary gain. I also have figures highlighting this risk aversion related to the objective function. I'll skip those for now in the interest of time. We can play around with carbon prices, which is a very efficient policy measure, as Emil here is nodding to. So what happens when we remove carbon prices? We immediately see that we really do not reach emission targets. However, emissions decrease a little bit as some low or zero emission technologies actually become cheaper than the established fuel technologies. So that's one thing. Then the second, what if we double carbon prices compared to the already high trajectory stipulated by the Norwegian government? Well, then we see at least something optimistic, and that is in all scenarios in 2050, we can reach the target of 90% emission reduction. But still, it's difficult to reach the target of 55% emission reductions by 2030. We managed so by 2034, but fleet renewal constraints and this technology adaptation make it difficult to reach targets already in 2030. So final slide of this presentation, maybe the most interesting one. This is a comparison between our approach with multiple time periods and the existing static approach. So everything where it says static, that corresponds to optimizing a transport system where you do not take into account these fleet renewal constraints, the technology adaptation. So you purely try to figure out what is the best system that we can achieve in a given year without thinking about how to get there. When we look at the figures for 2050, so figure B, D, and F, then we see that the difference between our base case, this stochastic case, and this static case, they're not so different. So we want to go to the same place in the future. But if we do this comparison for 2034, then we see that the figures are quite different. So we, when taking into account two developments over time, we achieve different transport systems on the way to 2050, and using a static model for planning, infrastructure planning, based on a static case for 2030 or 2035 will give misleading results in that sense. Okay, to conclude, we developed STraM, a framework for strategic national freight transport modeling that compared to existing literature and existing models adds multiple time periods, explicitly adds fuel technologies, and we include long-term uncertainty. In this presentation, I hope I convince you that it's relevant, and we showed some insights on various levels. There's temporal resolution, the nice geographical plots, and we show there is significant value to planning under uncertainty. There are significant differences to planning in a static way, and carbon pricing can be efficient when high enough. Currently, we're working on a more extensive case study for Norway to really provide insights for the Norwegian case. And here the main challenge is related to data. So we have to do a lot of verification with other partners to make sure that the input is as we want. And also we're looking into the connection with the energy system, which is maybe the main thing of interest for this audience. Is this is merely a sector model in the energy system, but we're strongly coupled to the overarching energy system, especially for the provision of the fuel technologies. So there is an interesting research area to be explored. Okay, these were the references I had during the presentation, and I'm happy to take any questions.
Thanks, Steffen.